I was a little bit skeptical of big changes in the Arctic Ocean in this area specifically, but in front of my eyes the picture is changing, and it's changing so rapidly that in 10 years the ocean became completely different. This is a completely different new Arctic Ocean. When I became a part of IARC, we had a wonderful spirit of camaraderie and friendship, and everyone from this time remembers this period. Everyone was friendly, was open, was collaborative, and I was really happy to be there, and NABOS was conceived as a part of this period of time. NABOS, this is our program, stands for the Nansen and Amundsen Basin Observational System. We were doing a lot of climatological studies at this period of time, and for that we used a lot of data to build climatological time series. It became immediately obvious to us that some parts of the Arctic Ocean are just empty, white spots with no data. Particularly difficult was that most of these white spots were in the Russian economic zone, where permission for observations is required from the Russian authorities. And since we had a lot of roots in Russia, we had a lot of friends, a lot of collaborators in Russia, it was pretty easy for us to organize this kind of project where we leveraged some decisions from the Russian authorities to support our research in the economic zone, and we continued that for many years. We started our program in 2002 with a desire to fill gaps in observational system. We were deploying instrumentation with the expectation that if anything happens in the ocean, we will see that. And we indeed found that our moorings showed very strong increase in temperature of the ocean interior in the mid-2000s. The Arctic Ocean has certain channels to conduct currents. They are called boundary currents. The major current system follows the topography. Where the topography is steep, that's where the currents are strong. This steep topography is associated with the transition from the shallow water area to the deep ocean. Key locations for monitoring fluxes of water from the lower latitude regions into the Arctic Ocean. And the time series showed that we were correct to place our instrumentation there and monitor major changes. We were not seeing any changes at the beginning of the program, and then in 2003-2004 we recovered several moorings, and when we plotted data we saw a very strong jump in temperature of the ocean interior. So the ocean started changing, started accumulating heat since the mid-2000s, and our moorings were tracing these changes. But that was not the end of the story. When we are talking about the Arctic Ocean, we are talking about several natural layers. One of the most important layers for the sea ice story is the Atlantic layer. Atlantic water enters the Arctic Ocean and it becomes an intermediate water occupying the depth range of about 150 to 900 meters. It carries a lot of heat from the Atlantic Ocean. This heat is enough to melt the Arctic sea ice several times over. But this Atlantic water layer, Atlantic water heat, is covered by fresh surface Arctic waters. The transition from the surface fresh water layer to Atlantic water layer forms a very special Arctic water mass, which is called the halocline. The stability of the halocline regulates how much of the Atlantic water heat penetrates the bottom of sea ice. In 2010s, we found that the halocline became weaker. That was the second and the most critical stage of the changing system. That's the key now. We want to establish and quantify how much of the Atlantic water heat penetrates the surface layer and reaches the bottom of sea ice, melts it and also warms the atmosphere. For our observations, we use a complex of instrumentation. Moorings we deploy in the Arctic waters monitor the state of ocean temperature and salinity and measure currents. Moorings are stationary devices which are anchored to the bottom of the Arctic Ocean. We put different instrumentation along this line, measuring temperature, salinity, currents, chemical properties, multiple parameters. We also use the so-called Lagrangian buoys. They are not anchored, they can drift with ice, and during this expedition we deploy several complexes of these buoys as well. ITP were invented a couple of decades ago, but now they are one of the major tools to monitor the state of the Arctic Ocean. ITP is an ice-tethered profiler. It is mounted on ice, but it has a wire below the ice in the ocean, 700 meters approximately, and there is a profiler which runs up and down along this line, measuring temperature, salinity, and sometimes other parameters if this profiler is equipped with additional sensors. Together, there are probably 10 buoys drifting in the Arctic Ocean, monitoring the state of the ocean. And this number of ITPs provides a valuable picture of the state of the ocean in general. But in addition to this oceanographic buoys, we will deploy ice monitoring buoys which monitor temperature and thickness of ice nearby ITP buoys. So it will be a complex of instrumentation drifting in the Arctic Ocean, monitoring the state, not just ocean, but ice as well. This program is one of the most important contributions of NABOS to overall Arctic community. We found, thanks to our observations and our collaboration with international colleagues, that the Halocline state is now affected by a strong advection of denser water from the Barents Sea. The halocline is weakening because the Barents Sea sends denser water into this layer, and as a result, the Arctic halocline becomes weaker and weaker, more penetrable to the transport of heat fluxes from the ocean interior. The weakening of halocline and the release of Atlantic water heat is the major message. This change is critical because it shifts the balance of forces maintaining Arctic sea ice from the atmosphere as the major driver to the ocean in the eastern Arctic. Manabe was talking about sea ice albedo feedback, where atmosphere interacts with ice and surface of the ocean and creates a very strong positive feedback mechanism, enhancing sea ice disappearance. But what we are seeing now is that ice albedo feedback became a part of a more powerful feedback, where ocean interior is involved. Our moorings tell us the story about changes of water temperature and salinity, but shipborne observations, including chemical observations, help us to identify the sources of water and produce chemical signatures of this water. That helps us to interpret physical observations with more insight into the nature of the processes driving changes in the Arctic. That's why the next step in our program is identifying the source of anomalous water in the halocline layer and to present the chemical signature of this water. If we want to identify the source of anomalous water in the Arctic Ocean or in any ocean, we need to operate not just with temperature and salinity, which are major parameters for physical oceanographers, but we need to work with chemists in order to understand the chemical signature of waters. Chemical sensors start appearing in mooring equipment, but these sensors are still extremely expensive and we don't have many of them. Instead, we use shipborne observations to take water samples for chemical signatures. Based on this chemical analysis, we can identify the source of water, whether it comes from ice melt or from Siberian rivers or from the Barents Sea. Critical for the program and for climate research is repeated observations. So we need to come to the same location year after year to see changes. And we are happy to report that our first mooring was deployed in 2002, and now we are sailing to the same location to recover another mooring and redeploy it for the next 2 years. Yesterday I calculated, and it happened that we maintained this mooring site for 20 years, repeatedly. I think it's quite amazing. I hope we will have this mooring for 5 more years, so it will be 25 years of observations at the same spot. I'm very proud of what we have accomplished. First of all, we were able to convince the international community to work together, and this is a great achievement. I'm really proud that I have colleagues, friends all around the world thanks to NABOS. There were a lot of skeptics who didn't believe that the Atlantic water heat is an important player in sea ice change because of preventive role of halocline layer. But now we have evidence that this oceanic heat plays an important regulating role to maintain Arctic sea ice cover, at least in this region of the Arctic Ocean.